What we will cover today, first one is reflection. Reflection with respect to y-axis, x-axis, and origin. And then from there, we will talk about symmetry with respect to y-axis, x-axis, and origin. And then from there, we go back to 2.3. We will talk about even and odd function. But these three topics are very closely related. And then I go to 2.4, we're dealing with basic functions. Our textbook called it parent functions. The basic functions we will be dealing with are absolute value functions, and then quadratic or square function, square function, and then square root, function, and then reciprocal function. Now then, if we have a chance, then we will do transformation. Seems like we will do a lot today, but each of them are actually quite small. Transformation, we will learn up-down transformation. You shift up, shift down, left, right. And if we have a chance, we will deal with reflection. Okay, but that's question mark. According to my timing, there's a chance that we go up to left, right, and up, down transformation only. And then on Tuesday, we continue with the further transformation. Okay, let's start with a small example so that you can picture the situation. Let's start with a coordinate 3, 4. Coordinate 3, 4. You know what? In case you want to have graphing paper and you don't want to go out to purchase, give me a second. Let me add graphing paper files. But of course, you need to print it out. You don't need to do it now. The one I give you right now, just the lecture. But when you rewatch the lecture, let's say at home, then you may want to have the graphing paper next to you. Okay, we definitely need our graphing paper on Tuesday when you come back. So print more, maybe. Okay, it looks like this. Oh, I already closed it. Well, it looks like when you do the preview here, it's one page with 6 graphing paper. 6 or 8. Yeah, 6 graphing paper. Okay, so print maybe 5 or 6. Okay, so that on Tuesday will be easier for you. Now, let's come back here. Suppose I have a coordinate 3, 4, and I want to reflect this coordinate with respect to the y-axis. So I go to the y-axis, and then from there I go further with the same distance. Now, what will the coordinate here be? Suppose we start from this 3, 4, right? And then I reflect that with respect to the y-axis. What will the coordinate here be? That will be negative 3, 4. Is that right? That will be negative 3, 4. Now notice that when you reflect with respect to the y-axis, the y component stays the same. Right? The y component stays the same. The x component, the one get the opposite. Are you with me? Okay, so if I reflect 3, 4 with respect to y-axis, that will give us negative 3, 4. Okay. If we reflect with respect to the y-axis, the x, the one, getting the opposite. Now, imagine if I reflect that with respect to the x-axis. If I reflect that with respect to the x-axis, notice that what will be the same? The x will be the same, right? The y, the one change.
Isn't the x 4 and the y 3?
Oh, what am I doing? Thank you, thank you. What am I doing? Let me change the graph. You're right, my bad. 3, 4 is here. So when I reflect that, it becomes negative 3, 4, right? And then when I reflect that with respect to the x-axis, the x stays the same, the y is the one changing. Is it okay? Right? So if I reflect the coordinate 3, 4 with respect to the x-axis, it gives the x stays the same, the y is the one get the opposite. Am I okay so far?
Wait, so basically, okay, so just for clarification, you're just saying that if it's x-axis, the y is the one that changed, and if it's y-axis,
yeah. But instead of like just thinking about what I say, take a look on the picture. Take a look on the picture. Okay, you see what I mean? So when I say that when you reflect respect to x-axis, then only the y change, it's actually from the picture. It's not that a theorem that I didn't tell you earlier. You know, it's actually from the picture. Okay, so imagine the picture. Okay, now
yes,
suppose we reflect that with respect to origin. Now, well, the reason I say that because I don't want you to make math into. I'm not saying you alone. I don't want my class and people in general think that math is a collection of a lot of theorem for no reason. Actually, there are reasons behind that. Okay, and the reason sometimes just as simple as observing this. Okay, now when I reflect this with respect to the origin, so I go to the origin, right, and then go the same distance the other side, what coordinate do I get? What coordinate is this?
Negative 4 and negative 3.
Negative 3, negative 4. That's right. Okay, so when I go respect to the origin, it gives me the opposite of the x and also the opposite of the y. Okay, now this is an example by observation. Now, in general, you will see the following. Suppose I pick a coordinate x, y in general, x, y. If I reflect coordinate x, y with respect to the y-axis, then the coordinate I get is the coordinate I get is the y stays the same, is it right? The x is the 1, I take the opposite. If I reflect that with respect to the y-axis, if I reflect that with respect to the x-axis, then the x stays the same, the y becomes the opposite. Right? Try to imagine that. So if I reflect that with respect to the x-axis, right, the x will be the same. Right, 6 down. The x will be the same. The y is the one get the opposite. Does it make sense, by the way? If you imagine the picture. Right? Okay, and when you reflect with respect to the origin, you will see we get negative x and negative y. You reflect both of them. Now, reflection with respect to origin can also be said as rotation. Rotate 180 degrees with respect to the origin. So suppose I have a rectangle like this rectangle. Okay, and then I reflect that with respect to the origin, I will get this rectangle. Where this coordinate here becomes here, right? And this coordinate here becomes here. Does it make sense? Which basically you can think of like we are rotating these 180 degrees here. Okay. So reflection with respect to origin can also be said as rotation with respect to the origin by 180 degrees. That's just another way to say it, okay? But when we reflect with respect to y-axis, no, that's not rotation, that's just purely reflection. When we reflect with respect to x-axis, that's purely reflection. Now, why do we want to learn this thing? Because of the following. There is one transformation that we will learn implicitly from here in 2.5. It is a reflection with respect to x-axis, respect to y-axis. While when they explain it there, seems to be complicated, okay? But the basic idea is actually coming from here. Suppose, for example, example 2. For example 2, I have let line 1 be 2x plus 3y equals to 6. 2x plus 3y equals to 6. Let's try to sketch the graph. 2x plus 3y equals to 6. The x-intercept is 3, 0. The y-intercept is 0, 2. So this is the line. That's the line. Okay, let me use blue color. That's the line. Now, my next question is find the equation of the line, the resulting line, if we reflect line 1 with respect to with respect to, let's say, x-axis. If we reflect this line 1 with respect to x-axis, what will the equation of the line be? Okay, but when we reflect with respect to x-axis, what do we know? When we reflect with respect to x-axis, your coordinate xy becomes x comma negative y, right? In other words, I will keep the x component. I will take the opposite of the y component. So the equation of line 2, call that line 2. So line 2 will have the equation 2x plus 3 times negative y equals to 6. All I do is changing the y becomes negative y. That's all I do. Okay, so the resulting line will be 2x minus 3y equals to 6. Now, if you want, you can try graphing this, right? Line 2. When you graph line 2, the x-intercept is 3, 0. The y-intercept is 0, negative 2. Okay, yeah, you can check this equation of this line 2. You will see that the equation of this line 2 algebraically, by algebra, this equation here has this graph here. In other words, our algebraic work confirms our geometric or graphic intuition. Okay. Now, going back to what we did up here. Now, then if I want to reflect a graph with respect to the y-axis, algebraically, what I need to do is take the opposite of x. Keep the y, change the x becomes negative x. Okay? Let's do one more. Let's do one more. Let's do one more. Let's say, for example, 3. Example 3. Let's say we have curve 1, y equals to negative 2 over 3x plus 1. Negative 2 over 3x plus 1. So the y-intercept is 0, 1. The slope is negative 2, run 3. Negative 2, run 3. Up to, run 3, up to, back up 3. So this is the graph of that C1, curve 1. Now, suppose I want to do the following. Reflect C1 with respect to, let's say, origin. Find the equation of resulting curve. Or in this case, it's a line. So let's see. if I do it point by point, this point I reflect with respect to origin, this point I reflect with respect to origin, this point 6 comma negative 3 becomes negative 6 comma 3. Negative 3 comma 3 becomes 3 comma negative 3. Okay, and then so on and so forth. So this is the resulting graph. Okay, if this is C1, if this is C1, this will be C2. Now look at C2. What is the equation of C2? From the graph. From the graph, okay, C2 is a line. C2 is a line with y-intercept 0, negative 1, and the slope is negative 2 down to run 3, right? So C2 is given by y equals to negative 2 over 3x minus 1. Now, notice that the way we get that is from the graph. The way we get that is from the graph. Now, how to do it algebraically? Algebraically, from algebra, okay, reflecting with respect to origin, gives from x comma y becomes negative x, negative y. Is that right? So what I would do is, if C1 equals to y equals to negative 2 over 3x plus 1, that's C1. Okay, then my C2 will be, I change the y becomes negative y. I change the x becomes negative x. Okay, I get negative y equals to 2 over 3x plus 1 divided by negative 1, negative 2 over 3x minus 1. Notice that this is exactly the same with what we had earlier when we did it by graphing. Okay, now what I don't want to happen is this then, oh Thomas, so you're saying that if I need to reflect with respect to origin or reflect with respect to x-axis or respect to y-axis, what I can do is actually I graph it, reflect that, and see what's the equation. No, that's not what I'm saying. What I'm saying is the graph confirm what we did earlier, such that in future I can get a function that I can reflect the graph of that function and get the equation without graphing it. Okay? Without graphing it. The algebra here. I change the y becomes negative y and the x becomes negative x as directed here. When we reflect with respect to origin. Okay, now with that said then, let's say for example, example 4, I guess, or example 4. Find the equation no, I don't want to say that when we reflect with respect to the origin, the only thing not changing is the slope. I will not say it that way because that only applies for a line. But the idea that I'm we are doing right now, we are not going into the lines only. Okay, it is true. When you have lines and you reflect that with respect to origin, then the slope. Actually, we can say this: if you have a line, right? If you have a line and you reflect that with respect to origin, then the slope will be the same. The y-intercept will be the opposite. Okay, I can say even more than just like keeping the slope. But the thing is, we are not dealing with only lines, though. If we are dealing with lines, I don't need to teach you this. Right? I don't need to teach you this. The thing is, we are going to do the following. Find the equation of the curve. Let's say x cubed plus y squared equals to 7 reflected with respect to let's say a with respect to the y-axis. With respect to y-axis, then what is the resulting equation? When you reflect with respect to the y-axis, the x will change, right? Negative x cubed plus y squared equals to 7. Negative x cubed plus y squared equals to 7. That's the equation. If you reflect that with respect to x-axis, the y will get the opposite. Okay? And then when we simplify, that's the resulting graph. Okay? Now that's the foundation for the work we will see in 1.1 and later on 2.3 and 2.4, 2.5. Definition. A graph of an equation, the graph of an equation, the graph of an equation has y-axis symmetry if, now there are many ways to actually describe y-axis symmetry of a graph. First, by intuition, when you look at that graph, okay, how it behaves on the right-hand side, the same way with how it behaves on the left-hand side. Then we say, oh, the graph have y-axis symmetry. Okay. For example, the graph that have y-axis symmetry that we know is the graph of x squared. That has y-axis symmetry. Agree? Okay. Can you tell me what other function that has y-axis symmetry? At this point, you're supposed to know two, but the one that I believe you're supposed to know is absolute value. That's right. Absolute value also have y-axis symmetry. Now, the thing is, there are many ways to describe y-axis symmetry. The one intuitively, if we fold along y-axis, if we fold along y-axis, then the graph match. Right? Okay, you fold it along this axis here, then this part will fold into that, this part will fold into that, so on and so forth. Right? But that's intuitively. Now, how to do it algebraically though? In other words, how do we know the graph of an equation has y-axis symmetry without graphing it? To go even further, okay, if we can tell the equation has y-axis symmetry, then we can just graph one side, and copy paste that to the other side. In other words, if you already have the graph, okay, doesn't matter you have y-axis symmetry or not, right? You already have the graph. You already have the big picture. But can we use the equation, from the equation, get the symmetry, then help us to graph? Okay, so the end points, the end purpose is to find the graph. If you already know the graph, doesn't matter whether it has symmetry or not, right? Okay, how do we come from equation to the graph? And can we find the symmetry to help us graphing instead of graphing to help us finding the symmetry? Right? Okay, so I did have that kind of question in the past, asking some students in intermediate algebra and college algebra, even in pre-calculus, asking them, how do you know that an equation has y-axis symmetry? And most students say, oh, graph it. I said, well, yeah, after you graph it, you can see everything. Right? But can you do it without graphing? And then they say, no, there's no way. Actually, yes, we have a way. And the way is this. The graph of an equation has y-axis symmetry if reflecting the graph with respect to y-axis gives the same graph. Right? So if you reflect, for example, absolute value, okay, so all the points here will go here, and all the points here will go there, right? Okay, if you reflect with respect to the y-axis, you get the same graph. Now, what will happen to the equation then, algebraically, if replacing x by negative x simplifies to the original equation. Okay, so the graph of the equation has y-axis symmetry if what you do is you flip that. You reflect that with respect to the y-axis. Okay, it is by replacing x by negative x, and see if you get the original equation. Okay, now likewise for x-axis symmetry, likewise to show that the graph of an equation has x-axis symmetry, we reflect the graph with respect to x-axis and get the same graph. Now the thing is, the process of reflecting the graph with respect to x-axis and get the same graph without actually graphing it. We do it algebraically. Okay, and how to do it algebraically? You reflect y becomes, you change y becomes negative y, and simplifies to the same equation. Is it okay? Now, let's look back here. Let's look back here. Notice that this equation in example 4, this equation here, when you reflect that with respect to x-axis, you get the same equation. Do you notice that? When you reflect that with respect to x-axis, you get the same equation. Then they must have x-axis symmetry. Okay? Then they must have x-axis symmetry. So in example 4b, okay, reflecting the graph of x cubed plus y squared equals to 7 with respect to x-axis, basically replacing y by negative y and simplifies. Give the same graph. Graphically, in parentheses, algebraically, give the same equation. So the graph of x cubed plus y squared equals to 7 has x-axis symmetry. Now, to explain this concept, all comes from this thing, all comes from this very simple observation in example 1. But we carry it through to learn how to reflect the graph of a function and what is the resulting equation. Okay, and along the way we pick up, if we reflect with respect to, let's say, x-axis and give us the same equation, then the graph has x-axis symmetry. Okay, now let's do one example that we know for sure has all three symmetry. Example 5. Let the curve be x squared plus y squared equals to, let's say, 9. What is this? This is the equation of what? That's the equation of a circle. Okay, center at origin. With radius what? Centered origin with radius 3. Okay, Now notice that the graph actually has all symmetry. X-axis symmetry, you reflect that upside down, you get the same circle. You reflect it with respect to the y-axis, you get the same circle. Okay, you reflect that with respect to the origin, you get the same circle. You pick any point on the circle, reflect that with respect to the origin, you will get something in that circle also. And it applies for all coordinates. Okay, now therefore, graphically, we know this equation, we know this circle has x and y and origin symmetry. Now, how do we show that algebraically though? Okay, so A, C1 has y-axis symmetry. How? When to have y-axis symmetry, you replace the x by negative x and simplify. That same equation, which means the graph must be the same. How about the x-axis symmetry? Replace y by negative y and simplify. Okay, you get the same equation. So has y-axis symmetry. Okay, this one here has same equation. So has C1 has x-axis symmetry. And if we want to claim origin symmetry, we replace the x and the y at the same time by negative x and negative y. And simplify to get the same equation. So this C1, this curve, has origin symmetry. Okay. Now you can actually play with this later on. Let's say I do number 28 from 1.1. So from number 1.1, section number 28, section 1.1. We have y equals to x to the 4th minus x squared plus 3. And the question is, check for the symmetry with respect to both axis and origin. Let's check x-axis symmetry. So to check x-axis symmetry, I replace the y by negative y. And when I simplify, actually, however I simplify this, if I have y by itself, I do not get the same equation. Not the same equation. So no x-axis symmetry. Okay. Second, the y-axis symmetry. To check that, I replace the x by negative x. So the same equation, I copy the same equation, I just replace x by negative x. negative x to the 4 plus, I'm sorry, minus negative x squared plus 3. When I simplify, I get x to the 4 minus x squared plus 3. That's the same equation. So has y-axis symmetry. And finally, how about origin symmetry? You do the same checking. Okay, replace the y by negative y. At the same time, replace the x by negative x. And see if it simplifies back to the original equation, which I don't think it is. It's not. It's not. Not the same equation. Okay, so no origin symmetry. Okay, now let me write a very little note. No, not that very little, but I think it's quite helpful. A note that is quite helpful. And it's not mentioned in our textbook though. Our textbook does not mention it. But with some observation, further observation, you will see the following. Okay. If an equation has two of these x-axis symmetry or y-axis symmetry or origin symmetry, then it must have all three. In other words, either it has no symmetry, it has no symmetry at all, none of these three, one of these three, or all three. It's impossible that it has only two. Okay? It's possible that it has no symmetry at all. Okay, for example, the lines that we have up here, like either C1 or C2, or even the lines we have up here, okay, L1 or L2, it has no symmetry at all. L1 has no axis symmetry, y-axis symmetry, origin symmetry, no. Okay. Okay. C1, C2 either, no symmetry at all. Okay. In this example 4, we have x-axis symmetry, but no y-axis, no origin. You can check the origin, but you will not see the symmetry. Okay. When we look at the circle here, it has all three, but you cannot find a case where it has only two of these three symmetry. No way. Okay. Now, suggested homework from this 1.1. Let me call this 1.1 star because I only do part of that. Or maybe I call that 1.1B, even though I didn't do part A. I did implicitly on the first day of class or the second day of class. I want you to do number 25 to number 31. Okay, just do the odd ones. That's testing the symmetry. Let's go back to 2.3. Oops, let me just do it here instead. 2.3b. We did 2.3 on Tuesday, most of that. And I leave 2.3b now. It's on even and odd function. even and odd functions. Definition. A function is said to be an even function if it has y-axis symmetry. The graph has y-axis symmetry. Okay. It is said to be odd function if it has origin symmetry. Okay, so you will see then, consequently, to check if a function is even or odd, you need to show y-axis symmetry, x-axis symmetry, and therefore, the way we check that is by replacing the x by negative x. That's for the y-axis symmetry, okay? And replacing x and y for the origin symmetry. For example, number 84. Hx equals to x cubed minus 5. Thus, is the function is hx even, odd, or neither? Now, to check if a function is even, what you want to do is, you see, I will replace the x by negative x. Okay, I will replace the x by negative x. Okay, I reflect that with respect to y-axis, right? And show that the resulting graph is the same to the original function. Okay? You replace x by negative x and show that the resulting function is the same to the original function. Now, if you can prove or you can show that h negative x equals to hx, then it is an even function. If I replace x by negative x and the resulting graph is the opposite, the y has opposite value, then it is an odd function. Replacing x by negative x give me the negative y. Okay, so you will see that what we are going to do here, how to show a function is even, how to show the function is odd, it's actually doing the same game again. To show a function is even, you need to show y-axis symmetry. How do you show y-axis symmetry? Replace x by negative x, you get the same y. You get the same function. How to show odd function? Origin symmetry. But origin symmetry means x becomes negative x, give the y becomes negative y. Right? So x becomes negative x, give us the y, get negative y. Okay, that's for odd functions. Now, how do we apply that concept here? Solution. See, take a look on h negative x. Actually, in both cases, to show if they're even or odd, in both cases, you do h negative x. And then simplify that, and see if you get the original function or the opposite function. You see that this is equals to negative x cubed minus 5, right? This is not equal to the original function. Even after you factor the negative out, that's still not equals to the opposite of the original function. So hx is neither odd nor even function. Number 88. Let fx equals to x square root of 1 minus x squared. Notice that I know that they don't have origin or y-axis symmetry. I found it. They don't have y-axis symmetry. They don't have origin symmetry. Therefore, they are neither odd nor even, not by graphing it first. Okay? So the observation, if it is with the symmetry in our class right now, is no longer by looking at the graph. Again, if you know the graph, if you graph that already, there's no point for us to ask about the symmetry or anything. You already have the full picture. Okay, but what if we don't have the picture? What if we don't have the graph? Can we find out about the symmetry? Okay, then we do these kind of things. Now then, continue here. Is fx even, odd, or neither? Solution. What we do is you replace x by negative x and see if it simplifies to the original function or the opposite functions. This is negative of x times square root of 1 minus x squared. Oh, this is equals to negative of fx, right? F negative x is equals to negative fx. So fx is an odd function. Okay, definitely not an even function because it's not equals to fx itself. It's equals to the opposite, but not equals to the original function, but not even. Okay. Now you will see in very, very general sense, in most of the case, a function is neither or odd or even. And one student once asked me this question, is there any function that is even and odd at the same time? Is there any function that is even and odd at the same time? And the answer is yes. Okay, I don't think I will ever ask this, but if you want to ask if your calculus teacher is actually prepared to teach pre-calculus, not calculus, then you can ask that person, is there any function that's even and odd at the same time? If that person say yes, means that person knows something, okay? And you may want to think about that. What function is even and odd? Now, somebody asked, is it besides circles? Is circle an even or odd function? Let's look back. Let's look back. Is a circle an even and odd function? At the same time, even and odd function. It has y-axis symmetry. It has origin symmetry. So is that an even and odd function? I'm asking. You think so? No, it's not. Why? It's not even a function. It's not even a function because it doesn't satisfy vertical line test. So the problem is not with the evenness or the oddness, it's the functionness that it has problem with. Okay, it's not a function. Does that make sense? So yes, it has all the symmetries that we discussed here, okay, but it is not a function. Okay, yeah, it's not a function. So that's why we cannot say it's even or odd function because it's not even a function, basically. But you are right, it has all the symmetry. Now, simply because it has all the symmetry doesn't mean it is a function, okay? Yeah. You can find something that really make you happy, okay, and it has 4 legs, okay, and never bother you. It costs you nothing, and it turns out it's not a dog, it's a table. Right? Simply because it has 4 legs doesn't mean it is a dog. It may be a cat. Okay. Now I'm saying that yeah, the problem is starts with actually it's not even a function. Okay, the circle is not a function. Okay. But there are actually a lot of equation. A lot of equation has all symmetry, not only circle. If you think about it, an ellipse also have all symmetry. An ellipse has all symmetry. You know, a hyperbola has all symmetry. The problem with these, they are not functions. They are not functions. Okay, there is only one function. There's only one function that, technically speaking, a function that's whose domain is all real number. That has even and odd symmetry. How about constant function, Thomas? Constant function, let's take a look. If I have constant function is an even function. But when you reflect that with respect to origin, it becomes down here. Yeah, this guy goes here. This guy goes here. You see? So it is even, but it is not odd. A constant function is not odd. Well, it's actually very close. The function that is even and odd at the same time is a constant function, but not a regular constant function. Okay, let me just tell you. A function that is even and odd at the same time is only this one, fx equals to 0. This function is even and odd at the same time. Okay, how do we prove that? Well, we know that for that to be even, f negative x has to be equals to fx. right? At the same time, it has to be odd, so f negative x equals to negative fx. That implies fx equals to negative fx. Does that make sense? Right? But if this is the case, means if I add both sides by fx, I get 2fx equals to 0, fx equals to 0. Okay? So fx equals to 0, not a regular constant, like fx equals 1 is not odd. Fx equals to 1 is even, but not odd. Okay, fx equals to 0 is the only function that is even and odd, whose domain is all real number. Okay, now that's for 2.3. Suggested homework from here is 2.3b, from number 83 to number 99. Just check even, odd, neither. Okay, that's all you need to know from this 2.3 further. Now let's go on to 2.4. In this 2.4, I will just describe some basic functions. Let me call it 2.4a. I don't really like the organization they did in this chapter 2, honestly. Because there's something from 2.4 that I would like to describe as a 2.5 instead. Okay, now 2.4 consists of, let's call that, two parts. The first part that I want to go over is called parent functions. Instead of calling them parent functions, I will call that basic functions. I will call those basic functions. The second is piecewise defined function. Now, I will do this. I will go over this. We'll do as part of 2.5. Okay, so what we'll do here, only the parent functions or basic functions. Basic functions, I need you to memorize. Are the first one, maybe I write it here. The first one is absolute value function. Y equals to absolute of x. Now, I believe all of you, if not most of you, if not all, already know what the graph of this absolute value of x look like. It looks like a V with vertex at origin and the slope is 1 to the right and -1 to the left of that origin. So it looks like this. Now, what I need you to remember is this: the vertex is origin. It has axis of symmetry. which is y-axis, right? Or we can also say x equals to 0. The domain is all real numbers. You can plug in any x you like. The range, however, will be from what to what? The range is from 0 to infinity. Okay, and the way you will graph that later on, you will do it this way. Please remember this. Please remember this. When I ask you to graph absolute value of x, I need you to give me at least 5 important coordinates. Now, those 5 important coordinates relates to this: 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Of course, if you can put more coordinates, it will be great. But at least the blue ones are the ones you need to provide me. Every time I ask you to graph absolute value, you need to give me these 5 coordinates. Okay? Just to give you, to illustrate what will happen. Now, some of you must remember this. Suppose I have y equals to absolute of x plus 2 minus 3. We will learn this in 2.5. Okay, so if you don't get it now, don't worry. But you have learned this also in intermediate algebra. So if you took intermediate algebra or algebra 2 before, you know that we can graph this by just looking at the equation. Okay, this means move 2 units to the left. 2 to the left, 3 down. Okay, it means if I have my coordinate system, the vertex moves from origin, move 2 units to the left and 3 units down. This is my new vertex. From that vertex, I build the rest of the coordinates. Move to the right 1, up 1, move to the right 2, up 2, move to the left 1, up 1, move to the left 2, up 2. So the graph of the line later on will be as the following. Now, especially if I give you graphing paper, then you can graph that more accurately. Okay, and from there you see, oh, the axis of symmetry is now x equals to negative 2. The domain is still all real number, while the range is now, because we move down 3 units, we'll start from negative 3 to infinity. Okay, that's a little glimpse of what we will do when we move it up, move it down. Let's see, the second parent function, the second basic function that you need to memorize is square function. Y equals to x squared. Y equals to x squared has vertex at 0, 0. When x equals to 1, the y is 1. When x equals to 2, the y is 4. Likewise, when x is negative 1, the y is 1. X equals to 2, the y is 4. You can just do it this way. You can create a table. When x equals to 0, y is 0. When x equals to 1, this is 1. When x equals to 2, this is 4. When x is negative 1, the y is 1. When x is negative 2, the y is 4. Okay, and you can go on. Negative 3 gives you 9. 3 also gives you 9. Right? So in long run, when you sketch this, the graph looks like this. Okay, that's what the graph looks like. Now, this graph has pretty much the same ingredient to the absolute value function, where the vertex is 0, 0. The axis of symmetry is y-axis, or simply x equals to 0. The domain is all real numbers. You can plug in any x you like, and you still get a real result, the real outcome. The range, however, is from 0 to infinity. Okay. So knowing this, suppose I ask you to graph y equals to x minus 2 squared, x plus 2 squared minus 3. Now, the original function, the basic function is y equals to x squared. Now, then, when you make it y equals to x plus 2 squared, this is move left, move 2 units left. And then from there, when you subtract by 3, it will move 3 units down. Okay. Now, pictorially, when I graph that, it will be 2 units to the left, 3 units down. From this vertex, 1, 1, 2, 4. That's what the graph looks like. At least by sketching. Okay, we'll do the more sketching in 2.5. For now, I just want to remind you that the important coordinates for this square function are these 5 coordinates here. Remember the movement: 1 to the right, up 1, 2 to the right from the vertex, up 4. Okay, now the third one is square root function. Y equals to square root of x. Y equals to square root of x. The graph of square root function is very similar to the graph of square, except that it is inverted and only one branch. So it's supposed to look like this if you don't require that to be a function. It's supposed to look like this if you don't require that to be a function. You see that it is an inverted square function, right? Now, but square root function, because it is a function, then it must satisfy the vertical line test, right? Okay. So instead of let's compare the to above. Instead of drag 1 up 1, drag 2 up 4, this time you up 1, drag 1, up 2, drag 4, up 3, drag 9. Okay, instead of this kind of movement from the vertex, drag 1 up 1, drag 2 up 4, drag 3 up 9. Instead of doing that movement, we invert that becomes from the vertex up 1, drag 1, up 2, drag 4, up 3, drag 9. Okay. Now, the important coordinates in square root function are these 3 coordinates here. Again, if you can add more, that will be great. In this case, 9,3. Okay. Now, the domain of this function is not all real numbers anymore. It's from 0 to infinity. And therefore, the range, as you can see, also the same, from 0 to infinity. It has starting point. Of course, we should not call that vertex. I call that quote-unquote vertex. Okay, it's not a vertex. It's a vertex means there's a symmetry. This function doesn't have symmetry. I call that vertex in sense of a starting point. The starting point is 0, 0. Okay. Now then, for example, suppose I want to graph this. For example, graph y equals to square root of x plus 4 minus 3. Or maybe minus 5. Minus 5, why not? Notice that originally it's square root of x, right? Now replacing x by x plus 4 will move it 4 units to the left. And then when you subtract by 5, you move it 5 units down. Now then, what will the graph look like? Originally, the graph looks like this. Originally, the graph looked like this. Right? It looks like this originally. Right? Okay. But I need to move this 4 to the left, and then 4 to the left, and then 5 down. So starting from this vertex, 4 to the left, 5 down. So now my vertex will be here. My new vertex will be there. From there, you build the rest of the coordinates. Up 1, right 1, up 2, right 4, up 3, right 9. Okay, so the graph of that square root of x plus 4 minus 5 looks like this. Okay, now then from there you observe what's the domain, what's the range. Okay, now last one, I have 2 more minutes. The last one, I need you to memorize this 4. I need you to memorize this 4 badly. Reciprocal function. Y equals to 1 over x. The graph is you can sketch, you can plot some coordinates first. When x equals to 1, the y is 1. When x equals to 2, the y is 1/2. When x equals to 3, that's 1/3. When x equals to -1 is -1. -2 is -1/2. -3 is -1/3. Okay. In fact, when x equals to 1/2, the y is 2. When x is -1/2, the y is -2. Now, if I plot these coordinates, it looks like this. Oops. That's what it looks like. Not supposed to touch x-axis there. Not supposed to touch x-axis. So the important coordinates here are 1, 1, 2, 1/2, 3, 1/3, 1/2, 2, -1, -1, -2, -1/2, -3, -1/3, -1/2, 2, -2. Those are the important coordinates. Okay, now I will stop here. Your suggested homework basically from 1.1D, 2.3D, and then memorize these 4 functions. On Tuesday when we come back, we will do 2.5 and studying 2.6. Okay, 2.5, we will spend some time there, I know, but then I believe we will have time for 2.6. Okay, see you then on Tuesday.
Thank you.